feature comparison for competing mobile apps leveraging user reviews. So do you have this? Do we have the speaker? Okay. So now let me start formally. So welcome everybody. This is the session on mobile applications one. It's in ICSI room 1. It's supposed to last for 1 hour, so from 9 to 10 a.m. Let me say Central European time, so my time zone. And I'm Luciano Baresi from Politecnico di Milano, and I'm supposed to chair this session. So the session should, if all speakers show up, should have 4 presentations, so 4 papers, 5 minutes each. So you know that this year the organizers has decided to have 5 minutes presentations at the beginning. So all presentations, one after the other, and then we will have, let's say, a kind of discussion or panel to discuss the issues related to the different papers. So I'm not sure, as I was saying, we have all presenters in this time slot. But let me start asking if we have the presenter of the first paper, so feature comparison for competing mobile apps leveraging user reviews. Do we have the speaker here? No. Do we have, and I think we have, the speaker of the second paper, so ModX binary level partial imported third-party library detection through program modularization and semantic matching?
Yes.
Okay, welcome. Well, I don't know where you are, probably, are you in China? Hello?
Yes.
Okay, so it's afternoon for you. Okay. Well, if you want, you can start your presentation.
Okay.
I think you should share your screen. Okay.
I have some problems with this Meet space because if I open my microphone, I can't hear you. So if you have something to talk to me,
well,
please.
I can use the chat while you are presenting.
Okay. Welcome everybody. My name is Yang Can. Today we are talking about ModX, a binary level partially imported third-party library detection via program modularization and semantic matching. With rapid development of commercial software, third-party libraries reuse has become popular. However, massive usage of the uncontrolled libraries will result in issues in the areas such as code auditing and in-depth understanding the risk of software supply chain. Existing feature matching-based approaches have 2 limitations. First, they embedded features from the entire third-party libraries.
So
Second, the compiler settings change the features of binary codes, which makes existing algorithms not robust. Here is an example where the bytecode changed and the syntactical features, which is strings, are removed. Hence, we propose ModX, a framework which utilizes a novel modularization technique to decompose the program and library into modules and to semantically match them to detect either fully or partially imported third-party libraries. It consists of 2 phases, the binary modularization and the third-party library detection. The classic solution of the modelization is the Giva-Newman and the following method. First, they define metrics to measure the modularity quality, and then they choose the best modelization, which achieves the best MQ over the whole network. Hence, there are three key points of modelization in binary programs: the design of MQ and the dividing policy, and the efficiency is important as well. We changed the original Giva-Newman MQ matrix from measuring the indirect graph to directed graph, since the function calls have directions. Also, we adjust the function volume by the number of statements in the function, so that when we modelize the program, we are able to begin with this heavy-weighted function to avoid generating models with only small utility functions. Based on the proposed modularity quality score, we used fast unfolding method to group functions. It works by calculating delta key for each merge steps. Here, there are 3 steps in total to know where is the best MQ and where to stop the merging. Moreover, to generate models with more intuitive, we add 2 biases to guide the modelization process. The first bias is the function entry bias. We would like to model the model to have limited entries to ensure a single and encaptured functionality. The second bias is the locality bias, which is a heuristic we added to let the algorithm consider the nearer functions first, rather than reaching to functions that are very far away. After modelizing the programs and the third-party libraries, we propose the similarity measurement to match modules. We use syntactic features and graph features and function features to detect the third-party libraries in the program. Here is an example of modules generated by human expert. It is generated from source code file. You can see there is isolated functions in the model, and the functionality of this is about string parsing is not complete. And this is the model generated by our tool. The functions are very relevant, and no isolated functions, and the functionality are more complete. We also select 7 metrics from different aspects to evaluate the quality of the generated models. The table shows, compared to the existing binary program modelization approaches, ModX outperforms other methods. We evaluate our tools on 2 sets of binaries. One is built with automatic Nix script, and the other built manually. In experiments, most of binary are partially imported, since the modern linker will only link the used portion of the third-party library by default. The semantic model matching and the partial library detection capability enables ModX to outperform other works. Here is the performance evaluation. In modelization time, ModX costs less time than BCD, which is another binary level modelization tool. And in detection time, since other methods use only syntactic features which can be indexed quickly, they have better performance than our tools. Also, we show that ModX has the best performance in malware detection accuracy, which is a more real-world case for partial code reuse detection. And we show that the modelization technique has the potential to aid the security analysis by providing modules which contain more vulnerability and are worthy to be further studied. For example, in OpenSSL project, we show that 3% of modules with 12% functions have over 70% CVEs. In summary, we propose ModX, which achieves a better performance in third-party library detection, and the binary level modelization technique also provides many new research opportunities. And thank you for listening.
Okay, thank you very much. As I said at the beginning, the idea, at least according to the guidelines, is to move all questions after the presentations. So now let me ask again, if we have a speaker for the first paper, so feature comparison for competing mobile apps leveraging user reviews. Do we have a speaker? No. Then let's move to the third one, and I think we have a speaker. So large-scale security measurements on the Android firmware ecosystem. And Qinsheng Hu is almost ready to present the work.
Yeah, okay. I will share my screen.
Yes. If you can also show your face, we would appreciate, if possible.
Hello.
Okay, now we see your face. Excellent. We might also see your screen soon.
Yeah. Can you see the slide?
Yes. If you switch to presentation mode, maybe it's even better.
Okay. Now I'm beginning. Okay.
Okay, please.
Okay. Hello everyone. My name is Qinsheng He, and the topic I'm sharing is a large-scale security measurement on the Android firmware ecosystem. This is a joint work by Shandong University, Qianxin Technology Research Institute, and Tsinghua University. Firstly, here is an overview of our method. We have collected more than 6,000 Zoom image files from more than 150 vendors and extract 440,000 APK files. In addition, we also collected more than 600 CVE vulnerabilities. Our measurement analysis focus on two aspects: the official patch, which mainly mirrors the patch delay and patch missing, and the pre-install app, including the actual impact of known vulnerabilities and the discovery of unknown vulnerabilities. The first is the patch delay measurement. From our measurement, we found that about 24% of images have patch delay issues, with the average delay time greater than 3 months. The worst case is from Oppo, and the patch delay time is as long as 40 months. In addition, we also found that 45% of Xiaomi's images have patch delay issues. For patch missing, we found that about 7% of the firmware has missing patches. The worst case is also from Oppo, which missed 46 security patches. In the firmware of Oppo, about 20% of the firmware has missing patches, and the average number is 1.5. From this, we can answer question 1 and question 2. For question 1, the security patch delay is widespread in Android phones. It means that the updated images of many vendors focus on the future update, not the security update. For question 2, the claims of vendors patching may not always be reliable. The possible reason is that vendors do not have sufficient testing time or cannot bear the maintenance cost. Next is the measurement of the actual impact of pre-installed apps, of the vulnerability in pre-installed apps. In this table, we can see that these 5 apps are all associated with undisclosed vendors. Therefore, the actual impact of pre-installed app vulnerabilities far exceed the disclosed impact scope. The last column of the table shows the compared time range of the associated firmware. These 5 apps were all disclosed with security vulnerabilities in 2019. We can see that after the vulnerabilities were disclosed, there are still many room images introduced the vulnerable apps. In addition, it can be seen that the security vulnerabilities of upstream suppliers' apps have a wider impact. At last, we have submitted more than 300 exploitable vulnerabilities in total. Among them, 38 vulnerabilities involving 15 vendors have been confirmed, and 32 CVE and CVD vulnerability numbers have been assigned. From this, we can answer question 3 and question 4. For question 3, apps with unfixed CVEs appearing almost half of vendors' room images. The affected vendors may be excessive trust in the code security of well-known suppliers. For question 4, all vendors' room images have potential security risks in the pre-installed apps. It may lead to multiple canned of the vulnerabilities. Okay, that's all. Thank you.
Okay, thank you very much. Again, I have at least a bunch of questions, a couple of questions, but again, let's move all questions to the end. Now, again, maybe while waiting for the first speaker, let's move to the fourth presentation. So demystifying Android non-SDK APIs, measurement and understanding. And I think that Xishuai Yang should be the presenter. Very good. Again, if you can see your slides and maybe your face, that would help.
Hi, can you see the slides?
Yes. If you switch to presentation mode, I think we can start.
Oh, hi. Hi, everyone. I'm Xishuai Yang, a PhD student coming from Shandong University. It's my pleasure to introduce our work on Android non-SDK APIs. This is a joint work with Ruili, Zhong Yichen, Wen Ruidiao, and Shan Qingguo. Non-SDK APIs, also known as private APIs, refer to that are not included in Android public SDK. There are mainly three forms: private APIs, hidden APIs, and internal APIs. Before Android 9, we could access non-SDK APIs through SDK replacements and Java reflection and GNI. But in Android 9, Google implemented access restriction on non-SDK APIs to increase app standard. However, there is current systematic survey on usage states of non-SDK API and the effectiveness of Google restriction. Our measurements contain three main steps. First, we constructed an APK dataset, including benign apps and malicious apps. Among them, benign apps come from 18 popular app markets, and malicious apps come from various total. Based on the source code of AOSP, we built an automated app scanner, Veridex++, and generated non-SDK API lists. To answer the proposed research questions, we designed multiple kinds of targeted analysis based on data constructed in previous steps. We mainly designed four research questions. The first one is focused on the effectiveness of Google's restrictions. Google restrictions on non-SDK APIs are mainly achieved by adding a runtime detection mechanism. The ART virtual machine determines whether an API call is a node to check the corner of an API and the tab of an API. In our investigation, we found that both double reflection and call stack breaking can bypass the restriction and throw in changing the identity of the corner. and continue to access non-SDK APIs. For our second research questions, we may focus the current state of non-SDK API. Non-SDK API are widely used and shows a growing trend, but only a small part of non-SDK API are always used between different versions of apps. In addition, we analyzed the reason for increased usage of non-SDK APIs. The first reason is the evolution of Android OS. Some SDK API used in the apps have become non-SDK APIs. The second reason is that third-party libraries may introduce new non-SDK APIs. Finally, the developers may use non-SDK APIs to provide ubiquitous functions and to increase the competitiveness of apps. For third research questions, we may focus whether there are significant differences in the usage non-SDK APIs between malicious and benign apps. We found that malicious and benign apps use non-SDK API are quite different. Only 4 API are the same in the top 10 non-SDK APIs used by apps. Furthermore, they use non-SDK API for different purposes. Benign apps use non-SDK API are mainly to improve user appearance, while malicious apps use non-SDK API to achieve malicious purpose. For example, malicious code loading. For the fourth research question, we are mainly focused evolution of non-SDK API in an Android framework. With non-SDK API are very unstable and change frequently, such as being removed from Android framework, and only few non-SDK API will become SDK APIs. We also investigate the reason for enhancing the restriction. The first is related to security concern. This API may violate user privacy. The second reason is to achieve more fine-grained access control over the API functions. Only a small part of API function is to provide it to the developers. This is the end of my speech. Thank you.
Okay, so thank you very much. Well, is the last call for the first paper. So do we have a speaker for the first paper? So the journal first one. No, apparently we don't have a speaker. Okay, let's continue with the other 3 papers and the other 3 speakers. So just to be sure we are on the same page, according to the program, the second, third, and fourth papers. Okay, let me try to define, well, a very simple process. We are just a few people, so we are some 10 people. So I don't think it's a big family. And then I would say there's no need for big rules. So if you have questions, you can ask, or you can enter the question in the chat, and then I can repeat the question to the audience and to the authors. Just to start, let me assume you are shy. I have at least, let's say, a question for each speaker, or actually a couple of questions. So let me start with the first one. So ModX. I do apologize because, well, I was not able to listen to the first couple of slides. But anyway, can you try to give us a couple of examples or a concrete case where your modularity solution, your similarity detection could help? So if I wanted to use your solution, how could I use that?
Some examples about how we use our solutions to detect
which kind of problems? Yes, which kind of problems can I detect?
Oh, okay. Let me share my slides.
Sure.
Here is an example while we are facing to analyze a malware. It clones a library libpcap, and it took us a great effort to recognize it. It have many problems to why existing tools cannot recognize it because the bytecode has changed greatly. You can see from here. And the second, the syntactical features like strings are removed by the malware, which is a common practice in malwares to remove these useless output strings to hide themselves. But how we finally find this malware uses the libpcap by analyzing it from a group. Here shows the red box is the functions in the malware, and above is the functions in the libpcap, which is the subroutine of pcap compile function, and we can see that they are very similar. So it comes from the idea to detect a group of function once in a time to detect which function or which library a binary is used. This is the problem or motivation example in our work. Hello?
Hello, can you hear me now? I do apologize, I'm having big problems.
Yes.
Okay, so, well, let me say, I buy the first answer. Then I have a second question for you, and then we can move to the other speakers, or we can see if the other attendees have questions. So if, you work on, in a sense, my understanding is that you work on similarities. Do you have a threshold? So do you think that, probably you cannot consider that you want perfect matches? Is there a threshold you are confident with, or you can be confident with, you work on? Because, I think that if the two graphs are too different, there's not much you can do.
Yes. This is a good question. Firstly, we base the similarity works, which our work is something to solve the function similarity works to achieve a better or average similarity average the similarity of the functions in a group or in our paper module to avoid some faults of single function similarity faults. This is the first advantage. And the second, we introduce two simple scores to describe the third-party detection confidence. In other words, the model matching, the model similarity, that what kind of model matching is the of high confidence that is true positive. The first is the model importance, and the second is library importance. The idea is simple. The bigger the model size, the more important the model would be. And the library importance is related to the library frequency. And the library has size. For example, we find many libraries are very small with only decades of functions, about 10 or 20. But this library matching will give us less library importance. And then we combine the similarity score with the library importance and the model importance scores to the final matching, to give a final matching confidence. This is the two approach we used to avoid some faults in the similarity methods. Thank you.
Yeah. Okay. Thank you very much. Sorry about my curiosity, but do you have an estimation of false negatives and false positives?
They have both. False positive false negative will affect our results. The false positive will match our models to the wrong one, and the false negative will make us perform bad in recall performance. We consider them both.
No, I understand, but do you have an estimation? So, for example, how many false positives did you identify in your experiments?
We can view this table. Here we manually compiled some examples, and we record the true positive, false positive, and false negative. The false negative is a little more than the false positive. This is maybe we introduce some strict method to filter out some matchings. Thus, we will miss something, but on average, we achieve a better performance other than the other two third-party library detection tools.
Okay, thank you. Let me move to the second paper. Well, in the meanwhile, now I do apologize. Maybe because of my connectivity problems, now we are 7 people. So you have me, you have the student volunteer, 3 speakers, and 2 guests, I would say. But anyway, so the second paper, which was about firmware patches and vulnerability. Well, I don't have an Android phone, but I'm very curious. You highlighted, if my understanding was correct, let's say the worst, in a sense, vendor or the worst case. But can you also give us some hints or some information on the best vendors? So can you give us an idea of the best phones or the best vendors which are used to patch the firmware of their phones?
Absolutely, I can. In our experiment, we have found that first of all, Google is the performance best, and even also we do have found some patch missing issues in some Google device, which confused us at the moment. But after investigation, we found that the vulnerabilities associated with the missing patch in Google device are all medium risk. And the reason is that Google no longer fixes the medium vulnerabilities in monthly security patch updates, but fix them in major version updates. Apart from Google, maybe Samsung and Huawei and OnePlus, you can trust them. Okay.
Okay. Again, let's say as a user, or I would say as a potential user, given, as I said, I don't have an Android device, but so given also that you said that there are different, let me say, severity levels. So my assumption, or my stupid comment, is that, you know, if the vendors don't fix these issues, it's because they think they are not important. So we can use most of the applications, or maybe every application, with no major issues. My understanding is that your results say something different. Is this correct?
Yes. Yes. Our measurement focus on the security patch and pre-installed apps security, which is, I mean, I mean, this is they are all provided by the vendors, and the user, when user buy the phone, when user buy the phone, the security status in of the phones are there. Yes. Maybe.
Let me ask you the same question in a different. So, how big is the problem? So, if I buy an Android phone and my vendor, whatever it is, decides that, you know, the firmware should only be fixed, I don't know, every 6 months. So, how big is the problem?
Maybe attackers, you know that Google publish the security patch every month, which make the vendors can fix the security patches in the Android system. If they don't fix these issues, attackers can use the known exploitable application to hack your phone, such as remote control or steal your privacy data.
Okay, yeah, I understand. But then let me add, and well, we have plenty of time. So, and then we have a question for the last paper, so the fourth one. So, according to your work, these are big issues. According to the behavior of, I would say, most of the vendors, they are not, because otherwise they should fix them faster than they do. So, who is right? what should I do if I own an Android device?
So sorry, I'm confused. Can you repeat again?
Yes. So if I understand it correctly, given your results, I think we have a problem. But given the way the major vendors behave, they don't see this problem, right?
Yeah.
So otherwise, they should patch. They should patch the firmware, let's say, faster or more frequently. Then, right?
Yes.
Okay, so that's that. Yeah, let me ask you the question, given what PayView is saying. So, what can we do with this firmware next? So, we know now we have an issue, and what can we do?
What can we do?
Well, besides saying, oh, now we have a problem.
Yeah.
How can we work on fixing it? What can we change?
Maybe we can push the vendors and submit the security issues.
So it's just a matter of pushing the vendors.
Yeah, and if you can't build Android apps your own, what we can do is only to wait the vendor to fix the issues. Yeah. Let me introduce some Google's policy.
Okay.
Yeah, I can share my screen. Okay. Can you see me slide here?
I can.
Yes. Yeah, Google for the security patch or the security or the pre-installed apps security, Google have published some policies to help the vendors to deal with the issues like the Project Tremble and STS, the security test suite. Project Tremble, which can push the vendors to update the security patches frequently and monthly. Yeah, and the security test suite, which is used to do the patch effectiveness testing. And if the vendor is a one partner, certified partner of Google, they must follow the above policies. Yeah, this is
Okay.
Google policies.
Okay.
Yeah.
Yeah. Since I definitely want to be fair. Let me now switch to the fourth paper, and also now we have two questions for the fourth speaker. So let me remind you that the fourth paper was about studying non-standard APIs for Android, again, applications. So those that are not part of the standard SDK. So the first question from our student volunteer is the following. Is there any benign app that is also using dynamic code loading, or is it just a sign of malicious behavior? Shishwai, can you hear us?
Yeah. Sorry, do you mean malicious app? Dynamic loading in malicious app?
Yes. So I think you can read the chat. So Iris Shu is asking, is there any benign app that is using dynamic code loading? Or if you want, the other side of the coin, is it a clear sign of a malicious behavior?
Let me show my slides. This is example.
Yes.
First, the malicious app can through a serious reflection call. This example, malicious code achieve malicious purpose. First, malicious app can serious reflection cost. Malicious code customize a class loader and reference the malicious code. A malicious app set the value of the class loader. The malicious app inherits from application. It starts to load the malicious code when the app is open.
Okay, but yes, but the answer to the question is different. So that's a clear example of, let me say, malicious behavior. But can I use, let me say, the same ideas, the same concepts in a positive way, so in a benign way? Or if I do that, it's only because I have, I want to be malicious. So is my question clear enough?
Can you repeat? Sorry.
Yes. So you have just presented an example of dynamic code loading, right?
Yes.
Okay. Now, in that example, we have clearly a malicious behavior.
Yes.
Are you aware of any example where you have the same concepts, so dynamic code loading, but it's used in a positive way? So there's no idea of being malicious, but just, to make the app work.
Such as many developers use dynamic loading to implement hot patch.
Okay. So, and these hot patches can be positive to the app.
Yes.
Okay.
This way.
We assume they are. There is another question, but I'm not sure I can fully understand it. So Pei Liu, does the app utilize the non-SDK APIs via the two approaches you provided in the paper? So can you, Pei Liu, help us understand the app you are referring to? Okay, so the app is the app you are working on. So the question, I guess, is, do we have examples of the two different approaches in real applications? I also agree with Quinn Sheng, who, in addition to security patches and pre-installed app security, we can also focus on security policies in firmware, such as the implementation of security protocols. And then we must hope that our firmware is patched frequently enough, let me say. Okay, let me ask you another, maybe simpler question. So you mentioned that you analyzed a huge amount of applications, clearly Android applications, but you have not provided any detail about these applications. Are these real applications? Are these, the applications we all use, or are these just, I don't know, examples or applications taken from GitHub repositories? So can you try to characterize, in a way, the applications you analyzed? Besides saying that you analyzed a huge amount of applications.
We crawled the application from 18 popular iPhone markets.
Yeah, but can you analyze any application even if you don't have the source code or the source code is obfuscated?
Sorry, I can't understand. Sorry, I don't get your point. Could you repeat this question?
Well, yeah, okay. The chart is working in the meanwhile. I'm just asking you, if you consider an Android application, well, when I distribute it, so I can maybe distribute the source code, I can obfuscate my bytecode. The application can be in Java or can be in Kotlin, and maybe there are also some other elements. So which kind of applications did you analyze or can you analyze? Do you need the source code? Do you need Java source code? What do you need?
Java. I analyzed the Java application.
And you need the source code? Or the bytecode?
Bytecode.
Okay, this means that if the bytecode is obfuscated, you cannot apply your solution.
Yeah.
And so your solution works on non-obfuscated bytecode.
Yes.
So we don't care if we start from Java or Kotlin because the bytecode is the same. Am I correct? Well, maybe yes. Okay, so given that we only have 2 minutes left. I can ask the attendees if they have a final question. And as usual, they can write it in the chat, or they can ask for it. Otherwise, I think I apologize again for my connectivity issues, but our support has just distributed a message saying that we are having network issues. Sorry about that. And also, I have to thank the attendees and the 3 speakers for their excellent works and excellent solutions. Let me also remind you that given this year's format, you can also listen to the long versions of these papers, so the long presentations, which are available on YouTube. So, said that, thank you very much. And I wish you all the best for the rest of the conference and for the future. Thank you. Bye-bye.
Thank you, sir. Bye.
Oh, okay.